So the next speaker is Lettie Roach, and she's going to speak on towards coupled wave ice ocean atmosphere interactions in climate models. Lettie, over to you.
Thank you. Hi, so my name is Lettie Roach, and I'm now at NASA GIS in Columbia University in New York. Thanks to the organizers for putting this on. They asked me to speak about flow size distribution modeling, which actually isn't something that I've worked a lot on in the past couple of years, but I thought now would be a good point to kind of review some of the previous efforts and think about how we can move forward. And I'd like to thank my co-authors on various parts of this work, including Cecilia Bitz, Chris Horvat, Sam Dean, Vince Cooper, and Ed Blanchard-Wigglesworth. So I will first give a little bit of an introduction, highlighting some recent results on sea ice and climate models. I'll give a review of wave ice modeling efforts, focusing on the work that I've been involved in. Then I'll talk about a recent study that we had in the special issue, looking at new observations of waves in ice, and then with a little bit of an outlook on moving forward with coupled models. So we've seen variants of this figure this week, but just to emphasize, obviously we've had a clear decline in sea ice area over the recent historical period. And the CMIP6 models, the latest generation of fully coupled climate models, there's quite some variation between the different models. Those are the various thin lines in this figure. But the historical sea ice area, at least in the multi-model mean, is broadly captured by those models. So next, I just want to mention a couple of studies that I think highlight some of the differences between these coupled models and observations. So the first we recently had published in GRL. This was led by myself with Ed Blanchard-Wigglesworth. And we used the CSM1 climate model that I think Marika discussed earlier in the week, which is a CMIP5 class fully coupled climate model. And this figure shows the September sea ice extent in its large ensemble, where we have 35 members that were initialized in 1920 with small differences in the atmospheric initial conditions. And so the differences between the thin lines on this figure show the internal variability of the ensemble, and the mean represents the forced response. And then Ed and I conducted a series of experiments that we branched from this large ensemble in 1979. And we nudged the winds in those model simulations towards values from reanalysis above the boundary layer over the Arctic, over 60 to 90 degrees north. And there's three different ensemble members that started from different initial conditions in red, and you can see that they're very close to one another, showing that the internal variability is really being damped out in this configuration. And they also really closely track the observed decline in sea ice extent. In this framework, we find that the model agrees very closely now with the reanalysis in a whole host of variables, including, for example, here, the near-surface air temperature trend. So I have the reanalysis, then the large ensemble mean, and then our nudged wind simulations on the third column in 2 different seasons. But if we look at the Arctic sea ice trend during other months of the year, so I have, again, observations, the large ensemble in blue, and then these nudging simulations in red, we find that although the September minimum trend is very well simulated, so the observed winds have driven an extra about 25% of the sea ice decline, as opposed to what you'd expect from the forced response alone. In the rest of the year, the model really struggles to get anywhere close to the size of the decreases in sea ice that we've been seeing. So highlighting that even when we have the right atmospheric circulation in this model, we cannot capture the sea ice trends most of the year, pointing to problems in either the ocean or the sea ice components. And then Ed had a paper last year looking at the high frequency variability of sea ice extent. This figure is for the Arctic, and this shows the CMIP6 models in gray with the multi-model mean in blue, and then the observations, in black, and then the observations are in blue. So highlighting that the CMIP6 models really underestimate the level of high frequency 3 to 10 day variability in sea ice that we typically associate with storms. And even it's not included on this figure, but even when we nudge the winds in the CSM1, this doesn't really improve that high frequency variability in sea ice. And then Ed also looked into the extreme sea ice extent changes, looking at 5-day sea ice gain events versus 5-day sea ice loss events. And so this is a composite from observations. And the basic story here is that these sea ice loss events are associated with larger ocean wave states and waves coming in the direction of the sea ice. And so one of the arguments of this paper was suggesting that the fact that ocean surface waves are not included in CMIC6 models might help explain the lack of variability in the sea ice. This might be becoming more important as the Arctic becomes ice-free. We've been seeing evidence of enhanced ocean surface wave activity in the new Arctic in observations, and this has been directly linked to the increasing open water areas rather than changes in winds. And this, of course, has direct impacts on Arctic communities. Yevgeny talked about coastal erosion, but storm surges are also becoming a big issue around especially the Alaskan coastline. And as I think we all know, waves influence sea ice. So we've heard about wave fracture. These images show thick multi-year ice, 350 kilometers from the ice edge that the authors in the study describe as being fragmented during a storm. And waves also determine how sea ice grows. So if the sea surface is flat, we form frazzle crystals, and that can form into sheet ice or nylars. But if the sea surface is rough, then we'll form these pancakes, which are a common feature, especially in the Antarctic marginal ice zone. And these processes, rather than affecting the typical variables that we consider in sea ice models, such as thickness or concentration, they affect the flow size distribution, which I don't think I need to introduce for this group. We've heard quite a bit about it, but from a large-scale modeling perspective, we think it's important because it directly determines the amount of lateral melt that occurs, because the total perimeter on the sides of flows is, giving you the total surface area that's exposed to the ocean. And as we've also heard, it has a lot of importance for rheology. So should we include wave ice interactions in climate models? And I think this question is still very open. So it would enable us to start projecting things like ocean surface wave conditions, which I think have a lot of relevance for local communities and potentially economic interests. We think there might be potential climate impacts through the impact on lateral melt, sea ice dynamics, and then there are also implications of including ocean surface waves in the Arctic Ocean in terms of their influence on wave-driven mixing in the ocean. But I think we don't yet really know if these are important at the climate scale, because we don't yet have fully coupled simulations with these processes turned on that we can really use to understand their impact. But I do think that trying to model these ocean surface waves and FSD processes across both hemispheres and across seasons has been a really interesting experience and really highlighted some of the processes that we don't know too much about. And so some of those considerations, I think, have motivated wave ice modeling efforts in a few different groups around the world, particularly over the past couple of years. And I will focus on the ones that I've been involved in. So we started from the theoretical basis proposed by Horvath and Zipperman, describing evolution of the joint flow size and thickness distribution. That's F of R and H. Subject to thermodynamics, mechanical interactions, and wave fracture. And they have some descriptions for some of those processes in that 2015 paper. And then during my PhD, I worked to incorporate that framework into the community sea ice model, SICE, which uses, as you've heard, an ice thickness distribution, so a probability distribution of ice thicknesses, which means that in every grid cell, we know that the fraction of ice belonging to different thickness classes, and that's discretized typically with about 5, or at least 5 different thickness classes. And that evolved subject to advection, thermodynamics, both vertical and lateral, with the lateral melt assuming a constant flow size of 300 meters, and then ridging and rafting, so mechanical interactions. And then we being myself, Chris Horvath, Sandine, and Cecilia Bitz, worked on including the joint flow size and thickness distribution into this model, so that in every grid cell, you'd know the fraction of ice belonging to different thickness classes and different flow size classes. And we did this in such a way that you could keep most of the model the same. So in our equation for the joint flow size and thickness distribution, a host of terms are assumed not to impact the evolution of flow sizes. So we keep the same advection scheme and the same vertical thermodynamics and the same ridging and rafting. So those are assumed to affect all flows equally. And then we made changes in the lateral thermodynamics and in the addition of wave fracture. So in this model, the flow size distribution emerges due to the interaction of 5 different physical processes. And there's a couple of citations here because we didn't get it, I think, really right the first time. It was a little bit iterative. In the Roach, Smith, and Dean, we looked at some observations to try and constrain those processes. But in the 2019 paper, we had new ice formation following Haley Shen, her parameterization that describes the size of new sea ice flows when they grow for the first time. Lateral melt and lateral growth following Horvath and Zipperman. We added in a flow welding, which is a simple coagulation scheme that happens during freezing conditions, as we needed more processes to restore the flow size distribution after it was broken up. And then we have wave fracture also following Horvath and Zipperman, which does typically, I think, give us the modal type distributions, like somewhat similar to what Fabian was showing. And then, so those are our 5 processes that build up the flow size distribution, but then only these 2 marked in red, the lateral melt and the lateral growth, then impact the sea ice concentration. And so in 2019, we ran this in a global model in size 5 with an ad hoc coupling to WaveWatch. So we ran the models sequentially and passed the information between them, forced by the GRA 55 reanalysis with a slab ocean model, nominal 1 degree, and this is a 15-year average that the results are from. And we used to do the wave ice interaction, we used the attenuation scheme from Malin et al., which has both scattering and dissipation. And so this figure shows the perimeter per unit ice area in the FSD model. And of course, this is in contrast to if you don't include this new physics, we'd have assumed a constant flow size of 300 meters, which corresponds to a very low perimeter. So now with this flow size distribution, we have areas of very high perimeter, very fragmented ice near the ice edge, those parts in yellow. And then we also have areas in the central Arctic where our flows are actually larger than 300 meters. So there's much more heterogeneity. We also compared 2 versions. The 2018 paper used waves as forcing, where we just had results from a wave hindcast that was done outside the ice and propagated them into the sea ice, but there was no interaction. So you're kind of missing the feedback of having more breakup and allowing more penetration of waves. And so we found that when we moved to the wave coupling, that we had basically more broken up ice and what looks like a larger marginal ice zone. We found this kind of interesting seasonal cycle in Arctic average flow perimeter, where we actually had a minimum towards the end of the summer, which seems to be associated with a lot of smaller flows having melted out by that time. But you can see that the new ice growth, so forming ice as pancakes, has a really large impact on the perimeter because you're growing really small ice. And the wave fracture was pretty important during the months where melt was occurring. So highlighting the role of wave ice interactions, but we're not really sure if this is really the correct behavior, and we don't have observations that show a seasonal transition. In some ways, I think of this as providing a hypothesis that would be great to be able to test with observations. So I was really excited to hear Ellen saying that she might be looking at the spring to summer transition. And then we looked at the impact on some other characteristics of Arctic sea ice. This is the difference in sea ice thickness between having a flow size distribution and no flow size distribution in July. And you can see that there are some large local differences, particularly at the ice edge. But we do find that as we enhance the amount of lateral melt that occurs, the basal melt reduces. And I think it's still unclear whether that's a realistic effect or not. We also were using a reanalysis atmosphere, so the location of the sea ice edge and its evolution is very heavily constrained by that. And so we think the impacts might be quite different in a fully coupled climate model. We kind of ended this paper talking about some observational needs, saying that we really need new large data sets to be able to kind of make further progress on model calibration and tuning. And so that's really where most of the model development work has sort of paused then in 2019. But since then, some things have happened. Thanks to Elizabeth, the code is available as an option in size 6 on GitHub, and I wanted to make it open access because I hope that people in the community might be able to take it and develop it further. The CPOM group included a representation of brittle fracture that I think Adam will talk more about later this afternoon. And they found, in comparing this, some individual kind of grid cells to some observations, that this seemed to improve the simulation of the flow size distribution. There's also been some progress in remote sensing, some work towards estimating the sea ice flow size distribution from satellite altimetry, although I gather there's still issues where the two different altimeters don't really give very compatible results. And Chris has been working on sensing wave heights in ice from ICET2, and there's also a recent paper by Brewer et al. And so these, I think, are promising ways forward, but we still only have a few years of data from ICET2, and I think those are still also in quite early stages. And then some work that was led by Vince Cooper, who's a graduate student at UW, used in situ observations of waves and ice. So this was a data set that we found out about through Jim Thompson, who's at APL at UW. And we're pretty excited to find this because these are multi-year observations. So there are a series of subsurface moorings in the Beaufort Sea that during part of the year in the sea ice cover. And from these, it's possible to extract the surface wave spectra. And so we were expecting to see in these observations this kind of cartoon with increasing distance into the ice of high frequencies being attenuated most rapidly in the ice and low frequency swells surviving deeper into the ice. But what we actually saw was in the first 100 kilometers, we saw a mixture of swell and local wind waves. And then beyond 100 kilometers, we saw a lot of these very high frequency wind waves, which we found follow a power law that suggests that they are fetch limited local wind waves. So we then went back to Vince went back to the model and looked at varying some of the parameters. So he looked at changing the attenuation scheme, and we tested a range of attenuation schemes within the IC4 module, which are mostly empirical attenuation schemes. And he also varied the scaling of the wind input with the ice concentration. and did a series of short runs and looked over that region and found that it is possible to capture the observed spectra in this top right configuration. But then we found that we're really not confident in how the wave fracture scheme responds to these local wind waves. We saw a lot of fragmentation, and we're just not sure that that's realistic. We also had a look at the wave-affected ice extent between these different experiments with different attenuation schemes. So defining the wave-affected extent as the area of sea ice with a significant wave height more than 30% and sea ice concentration more than 15%. So this is the enhanced wind input and standard experiments in the Arctic and Antarctic. And the dashed lines at the top are actually the ice extent, just to give you a sense of the scale. And then these different colored lines show the various generated by choosing these different attenuation schemes. And so I think there is some good news here in that the scheme that we were using, the Malin et al. 2020 scheme, if we compare that to the estimates from ISAT2, and I've said they're back of the envelope because I just converted them into an extent rather than a width. So I took the values out from their paper. So it's a little bit rough, but it seems that these actually do correspond quite closely to that FSD. That's we call it FSD scatters Malin scheme. So there is. I think that does give us some confidence in using that. And then thanks to the folk at NCAR, our code changes have sort of been propagated through. And so now we do have a configuration in CSM2 where we have the fully coupled atmosphere, WaveWatch 3 coupled to MOM6 and the sea ice. And so that's kind of in early stages, but Cecilia did a preliminary run using the fully coupled configuration in the pre-industrial control. And as I've said, we still think we need to do more model tuning and validation. But in this initial configuration, we are seeing really increased amount of extreme sea ice area loss. So there's 5-day sea ice loss events and that high frequency sea ice variability, as opposed to when you don't include the wave ice interactions. Okay, so in summary, even with the right atmospheric circulation, CSM1, widely used fully coupled climate model, cannot capture sea ice trends during most of the year, with the exception of September and October. CMIP6 models really underestimate high frequency sea ice variability, and that may be associated with the ocean wave state. We found in our modeling work that wave ice interactions seem to be particularly important for generating the FSD across the Arctic. And this new observational analysis highlights the potential importance of local wind waves within the marginal ice zone. So moving on from here, so we do have this advanced modeling capability for wave ice interactions in a climate model. And I should say it is pretty expensive to run with the wave model, but it's possible, and it's not the sea ice model fault. It's just that the wave model itself is expensive. I didn't have time to talk about this, but we do have machine learning tools to be able to emulate complex models. So when we run in the fully coupled simulation, we've been using an emulation of the Horvath and Zipperman wave fracture scheme. And we're starting to, I think, we're beginning to have access to relevant observations, but I think it's still a bit of an open question as to whether these observations are good enough to tune our model on. I think these flow resolving models are very cool, and it's been, I'm excited to see what other groups are doing in that space and whether we can learn from parameterizations based on those. We still have a lot of uncertainty as to how we choose our attenuation and wave fracture schemes, and these seem to be some of the more important issues for, or the most, have a lot of power in determining the flow size distribution. And then these, there may well be other processes we need to include, but yeah, I think it's still a question as to what those other processes are. And with that, thanks for listening, and I'm happy to take questions.
Thank you, Lettie. Great lecture. Questions?
Okay, yeah. I was wondering, do you have an estimate of like this high frequency variability, like from the observation? Because there's errors in the satellite data. So do you have an error bar on top of this that we can use?
I don't think there is an error bar that we could compute. I know there are errors in the passive microwave, but I think it's more in the sense of missing thin ice rather than necessarily changes in. There's a sea ice extent as well, right? So using the 15% cutoff, I think, does give us, I think my understanding is more that it's around the lower concentrations that we'd have a lot more error. We did, I guess there's only one line. I'm not sure if Ed used 3 products to calculate that line or just the one from the passive microwave. Yeah.
Thank you, Lettie. That's really amazing to see that waves are making their way into climate models, even though they are expensive to run. Have you considered including wave radiative stress, like the waves that can push on the ice? And you've done that.
Yes, so we have not actually turned that on yet, but I did do some simulations previously with the wave radiation stress from WaveWatch, putting that into the sea ice momentum equation. And so it's on our to-do list for the fully coupled model. That we have a lot of the framework set up, and that is a coupling variable, but we haven't actually put that in yet. But that's, it's quite straightforward actually to pass that in.
But with these results, have you seen improvement towards the bias between the winter ice extent compared to observations that you showed? Did your simulations that you presented have
so this was
closed the gap?
This recent one, it was just a pre-industrial control, and it's still very preliminary. We still, we'd like to get to the point of running into the historical period and checking that. But
thanks.
To do.
Thanks. It's a nice talk, Lettie. I was wondering, when you start coupling to the atmosphere, if there's any, say, new variables you couple to the atmosphere in terms of the wave to atmosphere, or maybe some new sea ice variables that need to be passed to the atmosphere?
Good question. I have not thought too much about that. So I'm using a configuration that Folk at NCAR have been working on separately. We've just really been focused on the sea ice wave part. But it's a good question. I have to think about it.
Yeah, I'm still a bit struggling to understand why you started with coupled model results, where you showed that the model doesn't get the trend right in winter time or most of the time apart from the 2 summer months, and how this relates to what is following. So do you think this is due to small scale processes and potentially due to wave ice interaction? This is missing in the model, that they don't get the winter trend correct? Or
I mean, I think probably it's more an issue in the ocean component, but I think there's potential for sea ice physics to play a role too. And I guess I didn't say this, but this work really, I think, highlighted to me that I feel like in the community we focused a lot on the September sea ice trend, but actually the fact that we're doing so poorly in the winter is something maybe we need to think about. I think there's always a lot of focus on September and the September trend.
Also enjoyed your talk. Thank you very much. I was wondering your perspective. Everybody's talking about flow size distribution and this implementation of that capability in climate models. At the same time, climate models with coarse solution have problems representing ice deformation. I was wondering how you feel about the relative, weight of
Relative
those.
importance. Yeah, I think there's just so much we don't know about the flow size distribution that I think it's really hard to say how important it is yet. And I would also say that in terms of resolution, the idea with this model was to be able to represent or parameterize some of these processes at the subgrid scale. Given that you have a, say, nominal 1 degree, that was kind of, we're not going anywhere close to the flow resolving with this. That's not really the right framework for it. But yeah, I think there's still a lot of questions here.
We have time for one last question, and I have a candidate.
I just wanted to go back to the original nudging experiment that you used. Did you test the sensitivity of where you applied that nudging over? Because you showed it was, I think, from 60 north.
Yeah.
I just wondered whether in the winter, when you're trying to capture those trends, whether you actually need to relax the atmosphere over a broader area further south to capture that.
So we'd actually initially did 45,
Okay.
poles of 45, but we had to be really careful because it has a really strong impact on the AMOC.
Yeah. Okay.
So we chose 60 to not mess up the AMOC, basically.
I'd better call an end to it there. If there are other questions, you can deal with them offline. I'd like you all to be back at 2 o'clock. We're not giving you a longer lunch or the same time. 1:55, okay. And the two speakers who are after lunch, if you could make sure you're here, well, the first speaker a little bit early,
Thank
just
you.
to make sure they can
Thank you.
set you up. Thank you very much. Great session.
I see a lot of performances. So certainly up at the top end rather than the bottom end. You're awesome.